All right, really nice question here. This is certainly an experiment I've done in class. I'm sure you have too. Okay, we're looking here at the analysis from the foam experiment where you stir some foam or pour it in and you look at the volume over time. Now this is used to replicate radioactive decay, and that's what we're looking at in this question. So let me just move things over. There we go. All right, so here's our data, and we're firstly asked to draw the best fit line. Okay, when you're drawing the best fit line, what you're trying to do is draw it within error bars. Okay, and this is my attempt here. It's not as smooth as you might like it. I've not drawn it in pencil, so if I'd done it in pencil, I probably would have had another go to make it a bit smoother. Okay, it must be within the error bars. Okay, now it says here to extrapolate your line to the v-axis. What that means is make sure that your line goes and cuts that v-axis. Okay, if it doesn't cut it, then it's not quite doing what we need it to do here. Okay, so now that we've done that, we're being asked to estimate the initial volume of the foam. Now you notice, because I've extrapolated my line to the v-axis, that means I can get the initial value, which comes out somewhere here. It's about 47. Okay, now in the answer, in the mark scheme, I think it says 48. They say expect 48. If you don't get 48, it doesn't mean that you're necessarily going to lose that mark. 47 is certainly close to 48. If you got 40, then you probably got a problem, because that would imply you've gone down. But I'd say anywhere between 46 probably and 50 is probably going to be all right there. Okay, the markers give those numbers as a guideline. However, it's not always something you stick to. And the point here is you're meant to be following this curved shape. Okay, which I've probably not done quite so much. I probably should have curved up a little bit more at the end, but that's the way it goes. All right, so let me just bring over here. We're then asked to use this experiment to try and model radioactive decay. And we're going to say that this thing should have similar properties. What does that mean? Well, if we double the time, then the volume should halve. So anytime t, if we take that volume and we measure it, and then we measure it after one half-life, it should be halving, and it should halve consistently. So that's what we're going to check here. We're going to use data from the BT graph to test the idea. That's quite a nice question. We first suggest the test, then we're going to do the test. Okay, I want to see if the student's suggestion is correct. Now, I started with 47, so I divided by 2, I got 23.5, and I found from my graph, and I'll show that in a second, that I got a delta T of 280. And then I went from 235 and divided by 2, and I got, make sure I got that right, 11.75, that looks right, roughly 12. Okay, and I found that took another 260 seconds. Okay, so the delta T is about somewhere between 260, 280, let's call it 270 seconds. It's within 20%, within 10%, sorry. Just to show you here, whoops, sorry, I drew things on here, did this twice. Okay, I used a very bad ruler, I'll be honest with you. You look at that, okay, make sure your ruler's straight, folks. Okay, to check my answer. Okay, so just make sure that you're drawing it on there, showing what you're doing, and make sure you measure it more than once. Do not measure it just one time. Okay, we're then asked finally to stop the experiment when the volume has decreased by 7/8 of its original volume. Now, I originally misread that question. I read it as 2, but they mean by. So basically, you've gone from V0 to V0 take away 7/8 to 1/8. So we're going to go from, we're going to say that our V is as a volume is the original volume times 1/2 to the power of n. Now, n is the number of half-lives. We're saying here that V over V0 has gone to 1/8 of its original value, so that's 1/2 to the n. Hopefully you can see there that n is equal to 3. So what that means is 3 half-lives have passed. 3 times my 270 gives me 810. So I'm going to suggest that 810 seconds should pass before we get to that value. Okay, now again, if you had a different value, I think in the mark scheme they said 280 for our half-life, that's absolutely fine. Okay, your value should be roughly equal to what they've got there. The important point is that you're identifying 3 half-lives, and therefore you're able to calculate 3 times whatever you have in this question. And so in my case, 810, if you did 280, it'd be 840. Okay, no worries there. You're allowed to have some freedom with the numbers.